It's linear algebra time. So here's the transformation. This guy here, I'm calling it T just to give it a name. And it's taking vectors in three-dimensional space to three-dimensional space. Notice this. Look at T. Look at just T. Don't look at anything else. Look at just T. Do you notice that the third row is equal to the first plus the second row? So what you know is that as a transformation from R3 to R3, T is going to lose a dimension. So let's see this in action. And there's a bunch of other stuff you know. What's the determinant of T? Rows, 0. Good. Does T have an inverse? Kyle. No, it does not have an inverse. Very good. So you can kind of think about how it doesn't have an inverse in terms of what T does. If T loses a dimension, how can you undo that? In math, when you send something to 0, you can't get it back. If I have a number, and it's a secret number, you don't know what it is, and I multiply it by 0, you know what I got? I got 0. Can you tell me what my original number was? It was 17. You can't get the 17 back. So if I lose a dimension, I lose a dimension. I can't get it back. There is no inverse matrix that's going to bring it back. So here's what I've got. I took this unit cube. So it's a cube with ones for coordinates. And here, and a cube has 8 corners. Here's all 8 corners. So here's the origin, 0, 0, 0. Here's 1 on the x, 0 on the y, 0 on the z. Do you see the family here? It's actually very combinatorial. It's every way that you can have zeros and ones in a trio. So that's your 8 corners. Now, I hit this matrix with this matrix. In other words, I'm using the transformation to send this box to a new place. So here's the multiplications. You can check them out yourself. It's all on the board. You can pause and try the multiplications and see how it goes. I have, take a look at it for just a second. Where's that weasel? Where'd you go? Weasel. Weasel. Where's the cocoa bananas? Come on, be with me. I thought I had a weasel in the picture. There she goes. There she goes. I'm going to get the weasel. Hang on. All right. We have been joined by Her Highness, Miss Cocoa Bananas. All right, so I hope you took the time to do a couple of these multiplications to make sure I'm not just saying stuff to you, that it's actually true. Now let's see where these points are. Well, the origin's the origin. 1, 1, 2, I have to go out 1 on the x, 1 on the y, and 1, 2, up 2 on the z. 0, 1, 1, I got to go 1 on the x. It's 1 on the y, 1 on the z, so that's this one. 1, 0, 1 is 1 on the x, 1 on the z, that's this point. And as I'm drawing these things, I'm thinking, this is not going to convince them that I'm getting a two-dimensional object. So here's what I did. I did 2 things for you. I did this for you so you would understand. Check it out. I have a bunch of points here that I claim are in a plane. Well, the equation of a plane is ax plus by plus cz equals 0. So I put in, well, first of all, the equation of the plane isn't 0 there, but if my plane goes through the origin, then that's a 0 there. So I put that in. And then I'm putting in numbers. I'm putting in 1, 1, 2 for x, y, and z. I'm putting in 0, 1, 1 for x, y, and z. I'm putting in 1, 0, 1 for x, y, and z. I'm solving this system. And it turns out that a and b have to be equal and c has to be negative of the other 2. So in other words, the plane has equation. You could have 5x plus 5y minus 5z. But the basic one is x plus y minus z equals 0. Now check out these points. Just understand that. That says that you add the first 2 coordinates and it cancels with the third coordinate to give 0. Let's see. Well, yeah, 0 plus 0 cancels with 0. But look at this. 1 plus 1 minus 2 is 0. 0 plus 1 minus 1 is 0. 1 plus 0 minus 1 is 0. 1 plus 2 minus 3 is 0. 2 plus 1 minus 3 is 0. Holy crap. 1 plus 1 minus 2 is 0. We did that one. Oh, here I'm seeing some evidence of a dimension lost as well. I got 2 different points that gave me the same point. So I've lost, I've got redundancy, put it like that. Anyway, this last one, 2 plus 2 is 4, minus 4 is 0. All these points satisfy this plane. All those points are in a plane. This transformation T took the coordinates of a unit cube and gave me a piece of plane, just a little piece of plane. Now, to top it all off, first, close-up of the ferret. There you go. Oh, such a good weasel. Now, the ferret's on top of something I'm going to show you. This is just the top of it. It's just a flat box. But here's what I did for you guys. I took a minute. Hey, weasel, over. No, don't jump there. I took a minute to actually plot the points in 3D. This is the z-axis. If you notice, the highest z is at 4. So I needed a z-axis to go up to 4. These bottom two connecting to the z-axis where my left hand is, those are the x and y axes. Okay, so see these blue points? Those are, I've got 1, 2, 3, 4, 5, 6 of them. I did remember there was 2 that were the same. So there's 7 to plot, but the 7th one is the origin, which is right here. Now check this out, okay? I'm going to take off the z-axis, and I'm going to lay this thing down on the blue points. Check it out. Oh. I got this. Can you dig it? Can you dig it? Let's get this in the picture here. Let's see. Oh, man. I want to get them all in the picture. I can get a better shot here. There we go. That's the whole thing. Oh my gosh, that's got to be a pretty convincing argument that all 7 of the points, if you want to say 8 because there's repetition, that's fine. But all 7 of these points are in a plane. So it's hard to say, make this plane look like a plane, but we can do it by equations or we can do it with a little model. So, big idea. T took a 3-dimensional space and sent it to a subset of 3-dimensional space. In fact, a subspace, a plane that goes through the origin. A plane that goes through the origin is a subspace of R3 because it's got the 0 vector and all yada, yada, yada. So T, as a linear transformation, sent coordinates in three dimensions to coordinates in 3 dimensions. It didn't just flatten it to the XY plane, but it did flatten this cube to a plane that is, you can see it as the top of this box. That's the point. So you have to think about this as, the origin's over here. So it's a tilted plane. It's a plane that's tilted. And here's the equation of it. Z equals x plus y. That's the equation of the plane. So I hope this makes sense to you. I hope that, and plus you got to see the ferret, so that's a good day.